This is Unit 5b. It deals with vectors versus scalars, and it also deals with the SUVAT equations. So starting at the bottom then, we've got our 6 bedrock ideas. Most of them, as you can see, are scalars, and only one of them's a vector. So the difference is vectors have magnitude and direction. You need these two numbers to describe them, whereas scalars need only one number, a magnitude. So we've got a couple of examples here. A crucial difference is there's only one way of combining scalars. So our example here is we've got 5 kilograms plus 7 kilograms is only ever going to equal 12 kilograms. There's only one way of combining them. In contrast, vectors, because of the direction element, there's 3 ways of combining them. So the example here is force. So addition is the most obvious one, but not the only one. So 3 plus 4 is 7. Subtraction, the forces could be in direct opposition to each other, in which case the resultant force is 1. Or they could be at 90 degrees towards each other, in which case we have to use Pythagoras, and we end up with 5 newtons there. So distance and displacement have the same unit, they're both meters. Displacement is the distance, the straight line distance from your starting point to where you happen to be, whereas distance is total distance covered. So this little rotating circle idea hopefully gives us an idea of what's going on. So that the total distance covered by this ongoing journey is only ever increasing, but the displacement is constant. So if that's the origin, the displacement is to there, and it is constant because the direction means that is changing. Now we move on to the SUVAT equations. So it gets its name from the sequence, the standard sequence of abbreviations down here. So S is displacement, which we've just been talking about. U is start velocity, V is end velocity, A is acceleration, T is time. Now we have 5 equations here. Now, perhaps slightly confusingly, but hopefully it will make sense later, these are the negative equations. So they're the equations that don't feature the quantity on the left. So let's go through these equations one by one. So the first one is end velocity is start velocity plus acceleration times time. Let's see why that makes sense. So if we look at this middle diagram here, middle graph, we've got our start velocity there. After a certain amount of time, we have gained some velocity, so that's this distance here, to end up at V, our final velocity. So if we were going 10 meters per second, our acceleration was 5 meters per second, and we did that for 2 seconds. So 5 times 2 is 10. 10 plus 10 would be 20. This next one here, we have displacement is Vt minus a half At squared. Let's have a look at these 3 graphs here. So Vt would be displacement if we had a constant velocity, or the start velocity was the same as the end velocity. So this area here, this shaded area, would be our displacement. Higher V, we'd go further, longer, more T, we'd also travel further, and we'd have a bigger area here. Now, in this case, we've got decreasing velocity, so U there is higher than the V, so At is still the loss, that's the loss in our velocity. So here we are, that would be our start, and we're subtracting something. Now where does this expression come from? Let's have a look. Now this red box here, the bottom line there is T, and as we've just said, this axis here, if you like, is AT. So T times AT is AT squared. So this red box here is AT squared. But this would not account for the fact that we have this starting velocity. So hopefully you can see this diagonal cuts through it exactly. So we don't want AT squared, we want half of it. Yep, we want to get rid of half of it, and that gives us this formula. Now in a very similar way, more or less opposite really, we have the UT situation. So start velocity times time, again that gives us this area here. Now we're adding, but by the similar logic, AT squared would give us the whole box, and we only want half the box, we only want the triangle, so we add that in. That gives us that formula there. This is another acceleration formula here. So here we have the average essentially. So u plus v divided by 2 or multiplied by half. So exactly the same way as you take an average of any two numbers, you add them up and divide them by 2 because there are two of them, and we multiply by the time. So this is, in essence, it's distance equals average speed times time. Obviously displacement and distance are different, but if it helps you sort of get your head around it, it's worth doing. This expression here is average velocity times time there. Now the last one is harder to visualize. You get it by substituting various formulas together, so it's not easy to draw a graph of it, but you do need to know it and you do need to be able to rearrange it. Now why was negative formula useful? When we actually do a real question, you would list what you have. So let's say you have S, U, V, and they're asking for A. Now you don't have T, you don't really care what T is. So this is the formula you would use. Right, just to repeat, they give you everything apart from A, but they want you to work it out, and they don't give you T. So that's why this is a good formula to use. It has all your knowns, it has your unknown, and it doesn't have the thing you don't know and don't want to work out. So there we have it, SUVAT formulas.